The differential equation dy dx minus y equals e to the x y squared looks linear except for that y squared term, and that makes this a Bernoulli equation. In particular, we're going to denote it's a Bernoulli equation with n equals 2, 2 being the exponent we see on y. In the case of a Bernoulli equation, we make the substitution u is equal to y to the 1 minus n. In this case, that means that u is equal to y to the negative 1, which means that y is equal to u to the negative 1, which we need for a couple of reasons. Number 1, we're substituting y. Number 2, we need to substitute dy dx. Therefore, we need to differentiate. Dy dx is equal to, we're going to use the power rule for u to the negative 1 and end up with negative 1 over u squared. Remember, when we subtract from negative 1, that exponent becomes more negative, and so we still end up with something in a denominator, but we need a chain rule times du dx. It's easy to forget the du dx, but I want you to remember that if you're replacing a derivative, we need to do so with something that contains a derivative. Now, making that substitution is going to give us negative 1 over u squared times du dx, that's in place of dy dx, minus y in this case is going to be minus 1 over u. And then on the right-hand side, we have e to the x times y squared. If y is 1 over u, then y squared is 1 over u squared. What we have at this point is an equation that's linear. And when we see a linear equation, we should be thinking an integrating factor mu. Now I'd like you to pause the video and finish solving this differential equation. Take it as far as you can, and if you can, back substitute to get the solution in terms only of y and x. I didn't quite finish it, but I'll catch you up and then we'll take it to the end together. We're going to clear the fraction by multiplying both sides by negative u squared. We end up with the du dx plus u equals negative e to the x linear equation that I alluded to before. We find that mu is equal to e to the x. The left-hand side is d dx times the product e to the xu is equal to negative e to the 2x. Don't forget we need to multiply by mu on the right-hand side as well. Integrating both sides is going to give us e to the xu is negative 1/2 e to the 2x plus our constant of integration. And isolating u gives us negative 1/2 e to the x plus c e to the negative x. Our substitution was that u was equal to 1 over y. And so u is 1 over y. I want to give an explicit solution. We're going to solve for y. In this case, that means finding the reciprocal. And we do not find the reciprocal of each individual term. It would be the reciprocal of the entire right-hand side, for which it would be easier if we had the right-hand side as one single fraction. So I'm going to rewrite the right-hand side e to the negative e to the x over 2 plus c over e to the x. And then getting common denominators is going to give us negative e to the 2x plus 2c over 2e to the x. If you've been watching my videos, you know I'm not going to leave that 2c constant as 2c. There's no reason for that. So I'm going to replace 2c using c. And also, if you've been watching, you know that means we've now changed the meaning of c, so I need to change the symbol of c in the previous steps. So I'll just throw in c1s there, and then everything's cool. Now we're going to find the reciprocal of both sides. We get that y is equal to 2e to the x divided by c minus e to the 2x. I think that's a good way to go with this one. Now we're going to see an example where it's not readily obvious that this is a Bernoulli equation, but it is. We have 3 times the quantity of 1 plus t squared dy dt equals 2ty times the quantity of y cubed minus 1. Using these variables here, we're looking for an equation of the form dy dt plus p of ty is equal to f of t times y to the n. I'd like you to rearrange the equation that we have to fit that form, and then we'll continue. Distributing on the right-hand side and then adding to get the linear term y on the left, and then dividing so that the coefficient of dy dt is 1 gives us dy dt plus 2t over 3 times the quantity of 1 plus t squared y equals 2t over 3 times the quantity of 1 plus t squared y to the fourth. We can see here that n is equal to 4. So our substitution is u is equal to y to the 1 minus 4, or y to the negative 3. I would turn you loose on this, but a lot of people make a common error at this stage. Before, when we saw that u was y to the negative 1, that meant that y was equal to u to the negative 1, but that's because u is the reciprocal of y, so y is the reciprocal of u. The common error I see at this point is if people see that u is equal to y to the negative 3, they're going to say, well, then y is equal to u to the negative 3. And that is not what happens here. This is the reciprocal of y cubed. And so to isolate u, we need to cube root both sides. So if we look at this as u is equal to 1 over y cubed, then cube rooting both sides is going to give me u to the 1/3 is equal to the reciprocal of y, so that y is equal to u to the negative 1/3. Another way to look at this is that if we have u is equal to y to the negative 3, I want the exponent on y to be 1. So I'm going to multiply the exponent, negative 3, by negative 1/3. Whatever I do to one side, I have to do to the other. Either way, we get the same result. At this point, I'm going to turn you loose on it, see what you can do, and then we'll come back together. Let's see how we did. And wow, that got colorful, didn't it? If y is equal to u to the negative 1/3, then dy dt is negative 1/3 u to the negative 4/3 times du dt using the power rule and the chain rule. We can then substitute dy dt using what I just read. Y gets substituted with u to the negative 1/3, and then we need to substitute y to the fourth on the right-hand side, and since y is u to the negative 1/3, y to the fourth power is u to the negative 4/3. So that's what we have on the right-hand side. And then we can see we can clear the fractions by multiplying everything by a negative 3. That clears the 1/3 in the first term. It changes the sign on both of the other terms. And then finally multiplying through by u to the negative 4/3 so that the coefficient of du dt is 1 is going to give us du dt minus 2t over 1 plus t squared u is equal to negative 2t over 1 plus t squared. Notice that the u completely disappeared on the right-hand side. We actually should always be looking for that to happen. Once we substitute a Bernoulli's equation and then simplify, what we have should be linear. And if it's not, then go back and look for an error. Since it's linear, we're going to use an integrating factor. Mu is equal to e to the integral of negative 2t over 1 plus t squared dt, which gives us e to the negative natural log of 1 plus t squared. That negative out front, I'm going to interpret it as an exponent on the quantity 1 plus t squared. E and the natural log cancel out, so I have mu is equal to 1 over 1 plus t squared. We multiply both sides of the linear equation by that. On the left-hand side, we have the derivative of the quantity 1 plus t squared times u. And on the right-hand side, multiplying negative 2t over 1 plus t squared by the denominator 1 plus t squared gives us negative 2t over 1 plus t squared, the quantity squared, which we then integrate using the power rule. We have the substitution rule going on, but we have a du in the numerator for that. So the result of integrating is 1 over 1 plus t squared times u is equal to 1 over 1 plus t squared plus c. Clearing the fraction gives us u equals 1 plus c times the quantity of 1 plus t squared. And since u is y to the negative 3, I'm just going to write down y to the negative 3 equals 1 plus c times the quantity of 1 plus t squared. That's our answer.